the way, Dennis and I zing each other on chat to make sure I start recordings on time.
Right.
Otherwise, it gets cut off. So we're now being recorded.
Very good. Is it okay for me to record this?
Yeah.
Yep.
Absolutely.
I think you have to give me permission.
Oh, to record? Oh, yeah. Let me see. I can do that, I think.
We're doing all the recording.
Okay, yeah, I understand that. Yeah.
Okay. He could record separately, just his part. So I gave him permission.
That's it. Yeah.
All right. I try now. I think I got it. I gave you permission.
Okay, good.
With my all-powerful host powers. Okay. All right. We're back. 2020 SARA conference. We've now got our next speaker is Peter East. Peter East, an engineer retired from a UK defense company specializing in radar and electronic warfare systems. He's authored a book on microwave system design tools and made several contributions to the SARA Journal. He's a longtime member of the British Astronomical Association and member of SARA since 2013. He's had a long lifetime interest in radio astronomy and made good use of his COVID lockdown. Grateful for the opportunity of researching low single noise SNR pulsar recognition. All right, Peter, from you're in where physically are you at now?
I'm in the UK, about 20 miles south of London.
Excellent. Okay, Peter, go ahead.
Okay. I'll just do my. There we are.
Okay, I see your slides. Yes, they look good.
Jolly good. Okay, well, good afternoon, everybody. It's a bit daunting to follow such an impressive speaker, but I'll do my best. This morning we heard some very good talks about detecting pulsars with very large dishes. So why is this talk about small aperture pulsar detection? Because it's possible, you might say, but no, the real reason is that I've got a small back garden and I can't get a dish in it. So that prompted me to see just what was the minimum sort of system I could produce that would detect a pulsar. So in this talk, I'm going to tell you how I collaborated with others. I didn't do it all myself, to check what minimum aperture was required, how to design a working system, the mistakes I made, so hopefully you won't make them, and the achievements of my betters, some results, but most importantly, how to be sure you've caught the fish. To add confidence with this, I've discovered a new half-fold correlation algorithm that points a finger at a good pulsar acquisition. I got interested in pulsar detection about 5 years ago in the SARA forum. Am I talking too loud, Rich?
Perfect.
Okay, yeah. So prompted by an unresolved discussion in the SARA forum about pulsar, the feasibility of amateurs detecting pulsars. About that time, I'd finished some hydrogen work, and whilst I was doing it, I was collaborating with a young engineer in Argentina who happened to be looking after the two 30-meter dishes in the Argentine Radio Astronomy Institute. His name was Guillermo Gancio, and he'd also done some work on detecting hydrogen. And we were both using the RTL SDR, which we heard about this morning. So I shot him an email and I said, could you point your dish at Vela and collect me some data? And then from that, I maybe work out what was the minimum receiver you needed to be able to detect a pulsar. And this he did, and with the result was, after a lot of work tuning software, let me see, was this, popped out of the noise base. The thing about this is if you get the period wrong, you don't see anything. It's got to be nearly right before you see anything, but it's got to be exactly right to get something like this. So from this, we chatted together and we worked out that based on the performance of his 30-meter antenna and the receiver that he had, and using the same SDR, that we needed probably at least a 3-meter dish, 3 or 4 dongles bandwidth, and several hours of tracking integration to be able to get a pulse about 1/10 of this size. So we followed on from that. I think I missed the slide, yeah. So what I'm going to talk about today is, first of all, I'm going to run through the radiometer equation, the pulsar radiometer equation, just to see what's theoretically possible, and then look at the key system drivers, what we need to, how we need to design a system to be able to detect the pulsar, look at what receiver components are available. Software is a bit of a problem here because there's a lot of specialized software, but there is a lot of software available, and I'll talk about that. And then I'll go on to present some results and how to validate that you have got a pulsar detection. Our next slide, I was going to tell you a bit about Pulsar, the Pulsar Basics, but that's been well covered this morning. But what I will say that Jocelyn Bell, as she was then, she discovered the pulsars, it was 53 years ago. But her antenna was 2,000 dipoles, as we heard this morning, and 16,000 square meters. And if you want to know what it looks like today, look behind me. That's her array, or what's left of her array. I actually visited the place a couple of years ago and managed to take this picture, and I thought it would be very appropriate for today's conference. Okay, so when you're looking at the detail of pulsars, you need to know what their specific characteristics are. We heard this morning they're very high stability, and there's a fairly regular pulse train. The rotation rate and the period is Doppler shifted by the Earth motion, so on a day-by-day basis, you have to make some period adjustments. It's basically broadband noise and a bit more powerful at the low frequencies than it is at the higher frequencies. It scintillates, you know, passes through the universe, and the amplitude hits electrons and things like this, whatever's in space, gradually. And so in fact, it varies in amplitude with both frequency and time. It's dispersed, we heard that this morning. The lower frequencies are delayed on the higher frequencies, and it's very, very weak compared to other radio astronomy sources. So this is the Lorimer-Kramer radiometer equation. The way I presented it here is SNR is signal-to-noise ratio. The signal-to-noise ratio, and I'll just pick out the main components. There's the pulsar mean flux, the antenna aperture, the integration time, the RF bandwidth, and the receiver system noise temperature. They're the key parameters. The factor on under the square root sign accounts for the fact that the SP is mean power and it's a pulse, and so to a certain extent this is a measure of the peak pulse power. But it also implies that in the analysis that you do, that the final processing bandwidth is restricted to just past the pulse. So a 1 millisecond pulse, you need a 1 kilocircle minimum bandwidth. It's implied in this. But this equation is making the assumption that you are tracking the source. When you have a small aperture, you have a wide beam width, and it's best to work in the drift scan mode, where you point your antenna at the culmination point of the pulsar and let the Earth scan you across. If you do that, then this equation is modified, and this is a drift scan version. It's exactly the same equation, but I'm just taking into account now that the antenna aperture is, the beam width is now frequency dependent, and because it's the Earth's rotation, then the integration time doesn't come into it. It does come into it. You need to record for the total time that the pulsar is within the antenna 3 dB beam width, and this factor 736 takes that into account. So it's modified slightly. There are two other factors, as well as the system noise temperature, the bandwidth. The frequency, I said, is more because for a given aperture, the beam width is frequency dependent. So that's why that factor comes in. There's a factor B, which is a factor less than 1, and it accounts for the fact that the beam width roll up at the edges is 3 dB down, and so you don't get the full power for the scan time. And this other factor R is if the antenna you're using has an elliptical beam shape. I'll show you later that you could have a wide azimuth beam shape and a narrow elevation beam shape, and if you do, then that factor R is the ratio between the two. Now I've used this equation to put in for Vela, the strongest pulsar in the southern hemisphere, and BO329, the strongest pulsar in the northern hemisphere. And here I've got signal to noise ratio against the aperture, the effective area in square meters. We're assuming a very good system with a system noise temperature of 100 degrees Kelvin and a 2.4 megahertz RF bandwidth. So this is the curve that we expect. So you can see that with a 1.5 meter squared aperture, you ought to be able to get about a 10:1 signal to noise ratio for BO329 and a 20:1 signal to noise ratio for the Vela pulsar. These two lines at the bottom, the lowest one is at a signal to noise ratio of 3, and that's roughly the peak of the noise, the folded noise at the end of the day. And the next line is at a signal to noise ratio of 5, which you can be reasonably confident if you see a signal with a signal to noise ratio of 5 that it's possibly a pulsar. But we'll go into that a lot later. So if you live in the southern hemisphere, you're about a factor of 2 better off than in the southern hemisphere. So that's theory. What about results? I should have said that was all at 400 megahertz, an RF of 400 megahertz. What's been achieved? Now, this blue line is assuming that you have a receiver tuned to 422 megs, a 2.4 RF bandwidth, and 100 degrees Kelvin system noise temperature. Now this in fact predicts the performance of an Italian radio astronomer, Andrea Dell'Imagine, who's probably the first pioneer of small aperture pulsar detection. And I'll go into it in a bit more detail later, but that's theory, and that was his result. Recently, he's used another antenna with an AirSpy SDR, and with the increased RF bandwidth, then the theoretical curve is raised, and he's achieved, and this spot shows his achievement with an antenna of 0.8 square meter squared. So you can see the theory and the practice, if you do it properly, lines up. If you don't do it quite properly, the bottom curve, the lowest one, is the result that I've achieved. I have a 600 meg RF, a 6 megahertz bandwidth, and my system noise temperature is a very high 175 degrees K. I still haven't managed I have managed on a couple of occasions to hit the line, but my average measurement is between 4 and 5 signal to noise ratio. So those are actual results against the theory. The bottom curve here probably explains why, with the Guillermo Gancio's data with his 30-meter dish, that we came to the conclusion that we really needed a dish with about 5 or 6 square meters aperture, 3-meter aperture, and this curve assumes drift scan mode, which the beam width is far too narrow at this frequency. But if you do tracking, then the curve rises above this, and you would get about a 4 or 5 to 1 signal to noise ratio. Okay, so that's theory and practice. What
Peter,
about...
One second, I got a question from Wolfgang. It sounds appropriate for now. It says, Peter, as you explained, your integration time is determined by the transit time at the source to your beam width. Have you accounted for the declination, which will have an impact on the transit time?
Yes, yeah, I'll come to that later on. Yeah.
Okay.
Yeah. So one of the important choice is the antenna, is the aperture, as far as I'm concerned, and that was the reason for the title. On the left, I show a horn. It's made of lightweight polystyrene material covered in aluminium foil. This is Rishi Patel's horn for 1420 megs. At 400 megs, the aperture would still be the same. We're looking for that sort of aperture. But to make a better match to space, it probably needs to be about 2.5 meters long. So it could be quite large and bulky. But a horn has got quite a reasonable antenna efficiency. The dish is, the parabolic dish is good with very large diameters, but at small diameters where the diameter is comparable to the wavelength, the feed blockage is far too much, and the efficiency and the total performance is very poor. An offset dish ameliorates this to a certain extent, but it's still probably not a good choice until you get up to about 3 or 4 wavelengths. Oops, go back. The Yagi has got a lot going for it. It's lightweight, easy to make. The electrical aperture is much larger than the physical aperture, but it's got some bad points, and that's side lobes. This is a plot of a professional antenna at 600 megahertz, and this is the E-plane beam width. and the beam width is roughly 28 degrees. The gain is around about 17 dB. Now, to understand what the effective side lobes are, if we make the assumption that these side lobes are at a level of minus 20 dB, the antenna beam width is 28 degrees. We know there are 41,000 square degrees in a sphere, so we can work out what energy is in the side lobes compared to the main beam by quite a simple sum. And it comes out that the efficiency of this antenna, assuming minus 20 dB side lobes, is about 66%. And what this means is that 34% of the energy is going in the side lobes. In deploying an antenna, we point it up to the sky at very high elevations. So most of these back lobes point towards the ground. And if we assume that, say, half of them point towards the ground, you can work out the ground is at 290 degrees, then half of them are pointed towards the ground, then the side lobe temperature can be as much as 50 degrees. If, like me, you have a small garden with a high horizon, my horizon is about 30 degrees, I've got the house quite close by, then this term could really get high. And this is the reason why my system noise temperature is so high. Unfortunately, the ARGI had a lot going for it, but it's not good for this application. There are other antennas that are much better that have got low side lobes, and other people have used these. This is the 3D corner reflector antenna, and that has an effective area of 5 lambda squared. It's frequency limited, so if you try to use it at high frequencies, then you just run out of effective aperture, because the sides are limited to a 3 lambda length, and that limits the physical aperture. So at 400 megs, the effective aperture is about 2.5 meters squared. At 600 megs, it drops right down to about 1.2 square meters. The other antenna that has been used, that Andrea Dell'Immagine has used recently, is the double biquad. This again has got good side lobes. This is a metal plane, and in operation you can put wings around the side to lower the side lobes even more. But similarly, that is aperture limited, and at 400 megs he achieved an effective gain of about 13 dB and a effective aperture of about 0.8 of a square meter. Oops. The other possible antenna, I don't know of anyone who's used this, but it was suggested to me when I did one of these presentations before, and that is the backfire antenna. The backfire antenna exhibits good side lobe performance. It's effectively a Yagi pointed at a reflector, and it's a resonant structure, and it's purported to have very high gain. So with high gain and low side lobes, it could be quite a compact solution. So what does a total system look like, a small aperture system? We can start off with our 3D corner reflector antenna. This is Andrea's 3-corner antenna. You'll see it's laid back by 45 degrees because in fact it produces a beam at 45 degrees relative to the bottom plane. So laying it back by 45 degrees effectively points it to the zenith. I've used a mini circuits low noise amplifier. This has 0.4 of a dB noise figure, and it can go right at the end of the antenna feed. This should be followed by a good filter. This is a 5-element interdigital filter that I made from data, from design data that is easy to find on the internet, and it worked beautifully. It has 6 megahertz bandwidth and over 50 dB rejection, with about 2 megs from either side. This can then feed into what I've shown here is 2 eBay amplifiers, about $15 to $20, purported to be 0.6 of a dB, but after low noise amplifier, these are more than adequate. And they feed into an RTL dongle into a computer. Now in operation, these are all connected together, of course. The data recorded, the data produced by the RTL is recorded on the PC, and this then goes into processing to recover the pulse. What I've shown here is a software package written by Michael Claassen, who lives in the Netherlands, and basically it takes RTL binary files and produces and does the dedispersion, folding, and data presentation. So that's basically all the system is. It's very, very simple. In my case, I wanted a wider bandwidth, so I've stacked a few RTLs together. I've stacked 4 here, but in fact, I only use 3. The RTL on its own has got some limitations. It drifts in gain and it drifts in frequency. The other thing is that it dissipates more power when it's recording than when it's quiescent. So the way to use it is to rip out the crystals, put in either a temperature compensated crystal to drive them, and that can give you half a part per million stability, or you can use a GPS disciplined oscillator. I've actually got a switch here that switches in either. And if you put heat sinks on all the major components in here, and you put lots of fans and pass lots of ambient air through it, then you can do a recording over 2 or 3 hours and the results are quite stable. Alternatively, you can use the AirSpire, and there are lots of other SDRs on the market these days, as we saw this morning in one of the talks. So we've got the system all built up. How do we test it? There's some free software, the SDR Sharp software. It accepts the RTL SDR, and it accepts other SDRs as well. And you can tune it for whatever bandwidth you require. And you can use this with your system to determine what the interference is like in the band that you choose. And in fact, it can also be used to check the sensitivity of your receiver system. There's the Y-factor method of assessing the antenna and the system noise temperature, and it's quite capable of doing that function as well. I saw you got Radio Eyes as a prize today. It's an excellent tool, and this is where I explain Wolfgang's question. You can in fact put the polar pattern of your antenna on this, and you can by modifying this, you can determine the time that it enters your 3 dB beam width and the time that the pulsar leaves your 3 dB beam width. And you can check this against the calculated time for the expected 3 dB beam width. And you can point it in elevation so that you get the maximum exposure. The other thing it can do, it has with the tools, you can program in and ask it to find the BO329, and it will tell you what time it culminates and how long you've got to wait for it. And so you can do all your planning with this bit of software. If you don't get it free, it only costs a nominal amount and it's well worth the value. So we've got our SDR. What does the data look like, and what does the processing got to do? But the first thing you have to do is to detect the video. The SDR samples the in-phase and quadrature components at the RF, and so you have to square and sum these to effectively do the square law detection process, and then you pass it through a low-pass filter before you process it further. And what I've got here is some of the data that I've collected. And what it shows is that the DC level of this component, because I've done a straightforward detection, the DC level is proportional to the system temperature plus the sky temperature, and it includes the pulsar temperature. The amplitude is now determined by the bandwidth of the low-pass filter. And in this case, the RF bandwidth was 2.4 megahertz. The integration time is a millisecond. And so there's about a 50 to 1 reduction in amplitude. Now, if you've got a 30-meter dish, you will actually see the bursts of pulsar noise on this plot. But with a 1 meter square aperture, you've no chance at all. It's the pulsar effective temperature is about 0.05 degrees. The peak amplitude is about 0.05 of a degree Kelvin per square meter per polarization. So for with a 1 meter squared, it's 0.05 degrees K. This is 2 degrees RMS. So the peak to peak noise is 6 times that. So that's 12 degrees RMS. And we're looking for a pulsar at 0.05 degrees Kelvin. And the way we recover the pulsar is the folding algorithm. Now, the folding algorithm can't be beaten. I've looked at lots and lots of processing methods to see if I can get a better signal to noise improvement than the folding algorithm, and you can't. Basically, what the folding algorithm does is it takes your data record over a time t, it cuts it up into exact periods of the pulsar, so that if you imagine, you can't see the pulsar, if you imagine the pulsar, it will always be in the same place in all of these blocks. And because this is now a digital signal, we can do with it anything we please. And so we'll cut them up and stack them all on top of one another. And the pulsar amplitude increases linearly. The background noise only increases as the square root. So the signal to noise ratio improves as the square root of the number of folds. And, you know, we're looking at, say, 10,000 periods, and the square root of 10,000 is 100. So it'll be your noise from the previous pulse will go back down by a factor of, effectively go down by a factor of 100. So what other software is available? Well, I've spoken for testing. We've got the SDR Sharp and the And for running on Windows, you'll need to download the Zadig driver, but all of this is available on the internet. For data recording, the Osmocom have produced a set of RTL tools. This is one of them. This is the one that collects the data, and that can be collected from Osmocom. For processing, I've written de-dispersion and folding algorithms, but recently Michael Claassen has developed these 3PT analysis tools that produces this lovely response. And I recommend anybody who wants to go into this field to download that from Michael's webpage. There's other software available. We heard this morning that GNU Radio there's some software written for that. For display, you can use Excel, MathCAD once you've got these downsampled C files. You can do your own programming, C and Python, and we're going to hear about AstroPi later on, tomorrow, I think. But the professionals have had a lovely suite of tools that are available. You can download them and use them. You heard about Presto this morning. Tempo is a software program where you can determine the pulsar period for any acquisition process you want to go for. So here's what I spoke about Andrea's system. This is his antenna again. He lives on a mountain in Italy, and I visited him, and it's a super site he's got there, but he still suffers from RFI. But his automatic observatory had running for 2 years, from about 2016 to 2018, and you could log into his web page and see the daily results. And with his system, he was probably the pioneer of small aperture pulsar detection. But with his system, as I said, he gets really good signal-to-noise ratios. It's quite easy to show that that is really a pulsar. His web page is very good as well, because this is the sort of presentation, the daily presentation he produced. I ought to mention his son, Giorgio, who actually designed and wrote the software for this page. And he's a young teenager, and he's impressive. But what it does show is the scintillation that I spoke about. So this is the recording time. There's not a lot of signal at the beginning and at the end, but this shows the scintillation. There are some periods where the pulsar is very weak, but the folding program integrates all of these. So to validate, the key thing with small aperture is validating. Is it a pulsar, or is it noise, or is it an RFI spike? With a strong signal, you can use the professional software and use the Presto pretfold plot, which I'm glad it was explained this morning. Here you can see the pulse. It's a nice, really big, strong pulse. This is the time waterfall. And it's interesting, you can see in here that there were periods of interference. This is the frequency one, and you can see there are, again, some background interference. The folding algorithm is very good at getting rid of small levels of interference. And if you look very closely, you certainly could see it in the presentations this morning. You can see a faint line down here, and the faint line actually is a bit clearer on the frequency scale. But if you look at the DM chart, the dispersion measure chart, you can see a very fine peak there. The dispersion measure for BO329 is about 26.7, and you can see that that is peaking up at the right place. The period scan and the period rate scans are a bit wobbly, but they do still show a nice peak in that area. And in the colourful plot, the cross is in the red. So from this, you can be pretty sure that that is a pulsar. RF interference, I've mentioned it a couple of times. There's so many sources of RF interference, and I've not got to the bottom of them. You can't identify where they all come from. But it's any modulated signals, digital TV, cell phones, transients, motor car ignition, people's hand tools, mowing machines, solar panels are very great interference, PCs, and large out-of-band saturating signals. What I'm thinking about there is that with my system at 600 megahertz, just above 600 megahertz are as an array of digital TV stations. And if the filter doesn't cut these out and they're still of large amplitude, the amplifiers we use, are these high electron mobility transistor amplifiers. They're usually very wide band. They'll probably cover from a few hundred megs to the low thousands, or maybe the high thousands. So there's gain right across this band. And so it's very important that A, you cut down the noise bandwidth by filtering, but B, you cut out these very large signals. So you need a good band defining filter and RFI mitigation techniques prior to folding. The Presto software has got a lot of easy to use tools that will remove RFI in time and in frequency. And they can also block out sections of bad RFI. But you've got to concentrate on identifying a low RFI band when you choose a frequency and you choose a band to operate in. The radio astronomy bands at 400 megs are about from 405 to about 415. But you'll notice that people have used 422. It's because there are some interfering sources in the radio astronomy band. So you can't always bank on that. But at the end of the day, the best results I've ever had have been in nighttime and early morning runs. And you've got to wait for the right time of the year for that.
Peter, 4-minute warning.
Okay, thank you very much. This is my system, so I'll race through it. It's twin Yagis. As I said, it was the wrong decision. This is I usually get around about 4.5 to 1, 4 to 5 to 1. If you look at the Presto plot, you look at the DM, indeterminate, period, indeterminate. The reason it's indeterminate is that they use this reduced chi-squared. And the point is that with low signal to noise ratios, it doesn't deviate the distribution very far away from Gaussian. So to validate weak signals, I've developed this 8-point check plan. The first test is it the right period and is it the right pulse width? And the blue dots are is a Gaussian pulse of the right one. So that looks right, but some of these noise peaks, they could pass that test. The next test is half file correlation, where you split the file into two. There's a lower half, a blue, the upper half. You fold them separately, overlay one on the other, and a pulsar should always overlap in the center. But as you can see, so do some of these noise spikes. So it's not a strong test. The other thing you can do is fold periods in pairs. So instead of stacking one on top of the other, you stack them on top of the other in pairs, and then you get 2 pulses in one fold, and you cut that in half, then overlay one on the other, and you see once again, this is there, and there are some differences in the others. I use 3 bands, so I can do 3 subband correlation. Once again, I get correlation at the right time, and there's far less triple overlap here. So subband correlation is a bit of a stronger test. The next one is period search. You do period search in Presto, but all you're looking for there is just an amplitude variation away from the correct period. This is changing the period by 1, 2, and 3 parts per million. But in fact, if you actually do the sums, you can predict exactly what the peak position shift should be. So as well as an amplitude profile, analytically, you can get more information. You can use Presto to do this, get this information, but it's a bit laborious. But you can do it separately yourself. So basically, as you increase the period away from the true period, the pulse broadens and the amplitude goes down. It happens less for noise pulses, but it's very clear. The other one is dispersion search, and you can do that manually. And once again, for dispersion search, you get an amplitude change which you can predict, and you can get a pulse width change that you can predict. Now, the work I've done that has been very interesting is I noticed that when you do half-fold correlations, that sometimes they correlate and sometimes they don't, but the pulsar always does. So I thought, well, let's multiply just the pulsar. If it's there, it's going to be positive. So let's just look at the positive side and multiply the 2 together. And if you do that, it gets rid of a lot of potential pulsars. It'll get rid of that one, for instance. Now, the other thing you can do is, as it's digital, you can split your half fold into periods. And then what you can do is I could take that period and put it there. And I could take that period, I could take that period and put it there. In fact, I could randomize all these periods. And then if I randomize them and then do a half fold, I'll lose some more peaks because the noise doesn't correlate, but the pulse always does. And if I've done that 50 times and produced this plot down here. So the red is the original fold, and the blue is the result of this half-fold correlation with 50 randomizations. And you'll notice the property that it's got is that the pulsar is always the same height, and it's always the right width, and it doesn't change, whereas the noise eventually all removes. To test it, I put in a simulated pulse. So with the live data, I added a simulated pulse at 3.5 to 1 signal-to-noise ratio, and did the same process. And you can see that both of those are there. This seems to be quite a strong test. I won't say that it's a 100% positive test. What I will say is it will pick out potential pulsars. I've done this with a number of data records, and it always finds the pulsar, what I think is the pulsar. Okay, so conclusions. Vela and B0329 can be detected in those low frequency bands using homemade small aperture antennas. The main design requirement is for a low antenna side and back load. All the rest of the components are easy to obtain. And understanding pulsar pulse train properties is key to identify low signal-to-noise ratio pulsars in RFI and noise. Thank you very much.
Okay, any questions? I think you answered Wolfgang's in the chat.
Yeah, and with Wolfgang's, you can actually calculate the time that it's in, so that you do need to program the data collection software for the right time.
Okay. I got a John Colt, great talk. Thanks, Peter. Great job, Peter, from Kevin McManus. So you're getting great job.
Okay,
And,
thanks very much.
yeah. Okay. Well, thank you very much. That was, I got an applause from Dennis Farr. Okay. All right. Let's go ahead and stop sharing.
Yep.
I think I'm actually up next. And
How do I go back?
there's been I'll zap you here. My all powerful.
Yeah. I've done it. Yep.
There you go. That worked. Okay, now I'll see if I can actually do it. After all this time, you know, trying to help the presenters do that, I've actually never shared my own. So we'll try that. Okay, can you get anybody see mine?
Yes.
Yeah, we got it. Yep,
Great.
looks good.
Great.
Got it.
All right, so a little self-introduction is a retired submariner and space systems engineer. And my last big gig before I retired was the chief architect for the Air Force Satellite Control Network. So believe it or not, I designed a lot of stuff, but I never actually played physically with the antennas. So when I got involved in the Deep Space Exploration Society, those guys actually put me in that antenna up the pedestal. And besides cleaning dirt out of every groove in there and that comm trailer, I learned a lot. And so now we're doing pulsars, and my goal in life as a retiree is to get as many pulsars as Wolfgang, and to write as many technical articles as Whitman Reeve. All right, so I'm in the right group here, trying to make a name for myself in the amateur radio astronomy community. All right, so as part of that, what I was, I got very interested, you know, our trips down to the VLA, that first SARA meeting we went to at the VLA really spurred my interest in the interferometry, the big interferometry guys. And so I started going to their technical conferences on processing the data to turn them into those pictures. And from there, you learn how to run the CASA program, and you learn how to do the VLA, the ALMA, and all the other big interferometry projects that you can process the raw data into those nice images. So so I took a number of those. I think I'm on my fourth one right now, over 4 years. And this is sort of the result. I thought it would be interesting. I'm not going to go through every one of these 100%. I'm just going to show you sort of the range you can get to if you want to play with these. And I was able to do it with a pretty high-end laptop. In fact, the Pulsar laptop we got was what really broke the broke the logjam in my head on how to do this with the CASA program, because it takes the same Unix, and you know, I had a terabyte drive and I had high speed and all that to run the CASA program with these large files. So it's so when you do get the high-end Pulsar stuff going, you can actually do the VLA stuff quite readily. So there are in this data set, so these big antenna systems do have they do store their stuff in archives, and so I have not yet got an official, and that's one of my future goals, is to actually put a request in to use the antenna for some astronomical phenomena, but I haven't done that yet. So meanwhile, I've been harvesting the data that's in the databases of these guys, trying to find neat items that I could process and turn into pictures. And what helps is that these guys also have tutorials that help you walk through the basic processes to get the the thing's done. So these are the 4 antenna systems. And I think that the what's cool is the European very long baseline is probably the largest overall extent, so the highest resolution version of that. Okay, and just to tell you, all my slides here are from my trips down there. So these are my pictures, so it's sort of fun to show these off too. Okay, so what did I need for this? The imaging and data reduction workshops. If you go to the NRAO website, and go under meetings, they show you these things. Now, the key is that if you want to go down to these things, or we just had the 17th annual synthesis workshop online this year, you have to have you need to get in early. They're free with the exception of some basic costs, and then you have to just pay you just have to get a hotel and travel and stuff down there. But basically it's basically free. The laptop though, one of the limitations there is you can use their computers, but if they have already got the sessions full, they're really limited by the number of terminals they've got down there in their rooms. So I actually brought my laptop and I was able to get in because I brought a laptop that I could just sit. I didn't even need their terminals. I can use my own, and they let me come in even though they were already full. Linux is pretty much what they're using down there, Unix, to run the CASA programs. But the CASA programs and the tutorials are all free downloads. So if you get that, you can start loading those and start working these things. There are right now there's 2, but more of these. But the 2 I use here is the VLA. You can select all sorts of menu items to select the object you want to look at. You can do it by frequency. You can do it by the axial position, various other things. And then the ALMA has a slightly different one. Actually, they have a nice star map. You can actually click the star on the screen if you actually knew where that was, and then it'll come up with the exact one. Plus, the other thing I use quite a bit on both these is that they'll actually show you the publication has been published for that particular image. So when somebody uses an image from any of these big antennas, one of the requirements is that you tell the NRAO what publication you used it in, so that they can document that and they get credit. A lot of times this is all free. If you actually do this, you can get, it doesn't cost you anything to actually observe on these antennas. You have to go through a science and you're competing, but once you get accepted, it's free, right? So how do these guys sort of make their money or make their fame? They basically, by the publication, how many publications, how much science was actually derived by publications from these from this data. So that's why. But they have that great database of publications. So the first thing I do if I'm going to do this, I go into the publications and look up all the different papers that use that image, and they're really neat to look at, and you can really figure out what that image is doing for you. Okay, everybody understands the RFI problem, but this is an example that actually was in one of the tutorials that this is it's by the way, this is amplitude versus frequency, and this is an example of what an RFI signal looks like, and that since it's basically when you get the data, it actually displays everything. So what flagging does is I can sit there and I can basically put a box around this and say flag, and flagging says, okay, it doesn't eliminate it from the database, but it basically turns it off as a source of data. And so if you look at that, and when I flag that thing, you see where the rest of the signal looks like in amplitude. So you could tell exactly that this thing would wipe out most of your data, but this is the levels that you're at here when you do this. This is an example of the EVLA antenna. I think it's in the, I keep getting a D or A, the smallest configuration. The configurations are, and each of these antennas are labeled as their physical antenna. Each physical antenna actually has unique attributes to it. They have different gains. They have different, maybe even some components to it. So they're all characterized very well in the computer as an individual antenna. And now the other thing to note here is that you have to pick out a reference antenna, and you try to pick one out that's in this somewhere in the center of this, because that's where the core is. Now, when I'm going to show you the next set of slides, this is an interferometer. So how does an interferometer work with multiple antennas? Well, basically, it does a beamform individually between each two antennas. So each two antennas has a separate beamforming, and then they add up all those separate antennas. So that that 27 antennas gets whatever 27 to to the nth is combinations on there. But this is all available online, by the way. So I didn't. What they'll do is that they'll say your antenna positions are available for that observations. Could have been 10 years ago they did it, but the antennas, where they were located, et cetera, are all available. And you have to do some calibration with these things too, because their actual positions, the calibrated positions actually have to be known for some of your data. Okay, this is at first I couldn't figure out how does a bunch of antennas actually form this image? How's the data being populated? And I don't know if you could tell, these two are dots here. These are, an example of two antennas. Don't worry about the equations or anything like that. Look at this chart here and this chart here. This is the actual, if I have two antennas and they're just standing still, the Earth's not moving, then I get sort of a pattern like this when you do a Fourier transform on it. All right, so that's just two antennas combining a signal. Okay, if I do 5 antennas, then I've got 5, each of those antennas, each of the 5 antennas actually talk to each other, and that produces a bigger, more detailed pattern. And you see where we're going here. 11 antennas, and then 27 antennas. So this is the max number of antennas for the VLA. Now, one of the key issues they always have is all these this extra signal that is happening, artifacts is what they're calling them. And you can tell here, one of the problems with the VLA is that you've got a lot of antennas that are in line with each other, and very few antennas that actually combine to form your outskirts here, right? So you get these very bright patches here, and in Fourier transform, that gives you a lot of artifacts that aren't real, right? So there's non-real data there, but they're bright because there's so many combinations of antennas that just happen to form a long line. So for the VLA, because there's three arms and they're not randomly distributed antennas, they tend to form these artifacts that you can almost immediately say that's from the VLA because I see the arms. Okay, so this is assuming, by the way, that the Earth is not moving and I am just looking straight on this antenna, all right, at the source. Well, the Earth's moving, but I'm tracking it, all right, and that gives me, you can sort of see that there's like 3 items here, 3. That's the sources that they're looking for right there, those 3 guys. All right. Now, how do I, that doesn't fill in very much. That's not a very dense pattern. So how do I start getting a dense pattern? Well, the Earth's rotation actually starts filling in the pattern. So you got that same thing, but now I'm rotating. This is a 2-hour rotation. You can start seeing how the pattern fills in, especially in the center, and even in the outskirts. I start filling in the patterns. You can see those sources are starting to pick up more because the density of you got to think of them as like pixels. The density of the pixels is increasing. I'm filling in the pixels in this this nice canvas here. This is a 4-hour rotation, so you can see how it's getting in more deeper, and the objects are filling in, you know, are starting to show up more. You start seeing those artifacts, and you start seeing that, you know, obviously that's the rotation patterns that you see. Okay, now that sort of gives you good, but this is with one frequency. Now, how do you fill in the other frequencies? Well, all of these baselines are based on your wavelength between the antennas. If I change the wavelength between the antennas, that means that I've got different, you know, different peaks in different locations for the same object, and I can actually fill in the holes if I use different frequencies simultaneously, and that's why these antennas have multiple frequencies and channels on them that they can do that. So so you look at this pattern, and then I go, okay, what if I have two simultaneous frequencies? You start seeing that thing really does start filling in those holes with the 2 frequencies and then 3 frequencies, and then you know, but you start seeing that that's how the interferometry actually fills in the holes to start making pictures. Okay. And I thought that was just I didn't produce this slide. This is Urvashi or Rao from one of the instructors in RAO. We presented this, and the light just came on in my eyes of how this all works. Before, I couldn't figure out how they make a picture out of a bunch of dots. Okay. All right. This is an example of one of the artifacts, and so this is all false color imaging. I can make any of the levels just about any color I want. So this is one of the standard colors that they use, but you can see that they actually calculates the primary beam, and then you can actually do contours for the different, you know, this is in Janskys per beam. So you can see how low we're at. This is 2 times 10 to the minus third is the top level, Janskys per beam, all right? And then you got a beam size. So this is an example of how low you can go on a screen, and this is the kind of results you get. Now you have to run a thing called clean, which basically does all your Fourier transforms, and it actually helps you pull out the signal from the noise and get rid of some of these artifacts that are sitting there, because these artifacts look like real sources sometimes. Okay, so what are some of the cool things? Well, I wanted to sample all the different, you know, something of each running this thing to see if I can actually produce a product. And I was looking for, you know, your basic products, you know, and then I was looking for how do they do the chemical signatures, how do you do absorption lines like you've had, etc. So the tutorials have a lot of these where they actually say, okay, here's an absorption line example, etc. Just download the following file and then do the processing, and it even walks you through the steps in processing. So a lot of these things are like that, and I actually show you which ones and do the links of what's processing and stuff like that. And then, okay, now by the way, this is the command center of the VLA. Not, you know, technically there's not a lot there. There's just a bunch of screens there, but they'll monitor the weather there. They'll monitor the location of the antennas. And one of the key things they do there is they do put a log together that says, okay, during this observation, and by name, by whoever the PI, the principal investigator was, what was the status of each and every antenna? Maybe one antenna, you know, was down for maintenance, or another antenna had a problem with one of the channels, etc. They will mark that down. And so that becomes a permanent record with that observation. And that's one of the first things they recommend you look at, because when you process the data, you can flag the different, and you know, by antenna, by frequency, by various other things. And if the operator said that that was down, the data still may be showing up, and you want to get rid of it fast because it's not really good data. So so that's what the operators do, and they have it's really automated. You know, basically, there's a team that puts together the schedule. These guys implement it. I think there's only 3 or 4 of these guys that do this for a living. And I understand the guy that does the midnight watch is a character. They've been doing that for years. Okay. Okay, this is my C5, a binary black hole. I think the two black holes are like over here, one there and one here down here. And one of the key things on this, I wanted to understand, how do you do polarization using the system? This thing will actually allow you to process polarization. So you can start seeing where the magnetic field lines are, this is, etc. Okay. And just an example of what I've got here is this top area is called the observing log. This thing is, you know, that the observer, the actual observer who requested this is Dr. Manuel Merijim, I believe, and what the date was and all his information. So it's very important, and this is the actual archive number. So if I wanted to go back to this exact binary star, I'd go to that number. So it's very important to actually acknowledge the observer who submitted the observation and got the observation. But after a period of time, they released the observation for the general public, because these guys, they got a time where they're allowed to have it for themselves so they can get their papers written and things like that. And then, but after that, it's open, and it's open in the archives. So most of the data is open in the archives, and just the newest data may not be open yet because they're still writing papers on them. Here I just tried to, because I'm in a total learning experience with especially I have more learning experience with astronomy or learning curve in astronomy than I do almost the RF stuff. So I actually tried to put together some kind of information, background information on what I was actually doing the data reduction for. So this is the actual thing I got built out of CASA. This is just background information from whatever source, Wikipedia or whatever. The tutorial, if there's a tutorial down here, the link down here works, and you go to the actual tutorial and download the same file and process the same file I did. So you can actually reproduce what I did by those links. This is a real cool one. It's called a tidal disruption event. Assassin, which is an amazing name for a tidal disruption event, but Assassin 14 Li. This is when a black hole eats a star, right? This is what it looks like, but that you can't see that star getting eaten by the black hole. This is just the location, what the VLA can see of that object. But if you look up the detail on it, it's actually, you know, the black hole, and then you got a stellar tidal disruption. They call it a tidal disruption, but it's fundamentally the black hole's eating the star. I thought it was really cool. But so I'm saying a lot of these things, just the pixel size and the size of the VLA can't see that level of detail. And I'm not quite sure what they've actually discovered that was a, you know, and that's where my learning curve is what is the actual thing that caused them to think this was a tidal disruption event. And I still don't know that for 100%. Cygnus X1, I think we talked about that. It's also a black hole. So that's a, you can see the different levels of the signal coming out of here, and that's the different contours. Cygnus X3, another black hole or a neutron star, they're not sure which. Same with M4, the GRO 0422 plus 32. Now you realize that when it says 0422, that's the right ascension, and the plus 32 is the declination. That's actually the first one I showed you guys. You see these extra contours out here. Those could actually be real, that there's actually some signal out there that's above background, or that could be an artifact of the antenna. Okay. Another black hole, a Q-type star binary. So this is a Q-type star rotating around a black hole. As I'm saying, you got to be better scientists than me to go figure out how they could tell that from there. But one of the key nice things about this whole process is that it actually gives you the detailed right ascension declination, and it'll do it in a FITS file. And FITS files, I could download a Hubble image and in a FITS file and overlay it with these images in a FITS file, and it will actually overlay them on top of each other at the right scale. Okay, I haven't done that yet, but that's one of my goals, that we could take all our radio astronomy observations and overlay it with all your optical or all your other observations from different radio sources, and you can start seeing a pattern emerge between the optical radio and everything else. And if you document what frequency you're on here, for example, infrared versus UV versus X-ray versus optical, you can start coming up with some science on those. Okay, and by the way, this is what the feeds of the VLA antennas look like. There's actually, you can see that's the low frequency, one of the low frequency ones, and then you got various other ones wandering around there. These, by the way, are heaters. That one of the problems they've got is that in the mornings, you got dew on these top of these guys, and that water is bad, so they put heaters on those to try to warm them up. I also learned that because of this white here, you can actually point this thing directly at the sun, and they use that to melt snow. There's also some antennas, I don't think I got a picture of that, right above this that are really dipoles, that they can start looking at the very low VLF kind of data. This is fixed. So how do they change? They've got a subreflector above this, and the subreflector is slightly warped, so that when the signal comes up, it hits the subreflector, and they can move the subreflector. It's on a motor, they can move it in order to aim the signal back down on any one of these, any one of these horns here. So that's how they can do it. And that'll also allows them to rapidly change frequency with the same observation, which was really an advantage for this antenna, is that you can sit there and run multiple frequencies just by moving the subreflector and bring down a lot of data with different frequencies. Binary supermassive black hole quasar. I thought that was the coolest, thing. And it's the EVLBI. So that was that one picture with multiple antennas all around Europe. But you can clearly see the two binaries here. 3C345, which is also, I think, a calibration source. So, you can also see the size of the beam. The EVLBI is a very high resolution because there's a lot of antennas spread all around Europe, and you get a high resolution there. So that was a really cool processing on that one. I just like the fact that saying binary supermassive black hole quasar, I just thought it was the coolest thing. Okay, Sagittarius A star. All right, so the binary, or the black hole in the center of our galaxy. If I think about this twice, I should have changed. I could change the pixel size a little better, but that's what it looks like. If you look at actual pictures of that, there actually is that angle there on this thing, but you can actually see it. And what you're looking at is you're looking at the accretion disk around it. You're not seeing the black hole. And all these black hole ones, you're looking at the accretion disk, or you're looking at the signal from the binary star that's rotating around there. So you're looking at the artifacts of that there's a black hole there, but you can't see the black hole direct, obviously. That was from ALMA. Okay, and there's a picture, by the way, of the subreflector on the VLA antennas, and you can't see it, but I did get a look at one of these things that was sitting on the ground in the maintenance bay, and there is a nice angle there somewhere around one of these guys. And these are in different dipoles that are up there to be able to get some of the low frequency components there. So they do have some of that available for everybody. Okay, Cygnus A. This is really nice because, you know, obviously the black hole is here, and this is the beams coming off the black hole. So those are actually, think of those as the you know, the beams that are affecting the interstellar matter on both sides of the black hole, and the things shooting out on each side. You're just seeing the artifacts of that, with the object that's in the center is actually causing all that to happen. So I did get that nice picture of that. It doesn't look quite the same as that picture, but I was able to get that pretty well there. If you're an expert at this thing, you get it done very well. You can obviously get really good pictures of this thing. I'm not an expert, but I was getting better. Also, what at least the ALMA does is they've got what's called a pipeline. VLA has it too. It's called a pipeline, and they will automatically calibrate and do all the flagging and produce a picture for you that you can either use directly as your science picture, or you can use that as a start off and then go and reprocess your own raw data. So my interest was in taking the exact raw data and doing all the flagging, calibration, and et cetera, and the images of it. This is a supernova remnant, 3C 391. And you can tell I'm trying to take some of the pictures here and say, okay, am I even close? And say, yeah, I think I was pretty close there. Because most of the time, I mean, part of my learning curve is I didn't know what these things are supposed to look like. So I basically had to go, I tried to find some kind of an image to compare them against. It turned out pretty good. This is the bottom. So you saw those horns on the top of the dish. This is the bottom of the. This is inside the bottom of the dish. So this where each of the horns came up. And by the way, there's a cryogenic cooler right here with the receivers in it. Very, very noisy. I mean, they're click, 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 click. Very noisy things. All right. And so one of the things I said, the biggest problem the VLA has in terms of cost is keeping those cryogenic coolers running. All right, so that's, you know, $1 million a year, I think, was the budget for those, just to keep them running. Okay, asymptotic giant branch AGB. So basically very this is a black hole that's very active in the center of a galaxy. And what I want to show here is the different frequency bands. So this is one frequency band, this is another frequency band. Same image, same dimensions, just different frequencies. So you can see that there's different things in there that you can see at different frequencies. So it's good to go and do multiple frequencies to get your science there, because there's you can just see different levels on this. All right. Gravitational lenses. Well, this has nothing to do with gravity except it's on a track. This is the mover that they move the antennas with. We got to see a couple being moved when we were out there. So very cool. And by the way, if you're a railroad person, they do have a railroad out there that they move these antennas. So they were doing railroad repairs last time we were out there. Black hole binary. Okay. Another black hole binary. So basically, you can see the two different binary objects here on this. Oops, sorry. Now, what I'm saying, gravitational lenses, and this is a prime example of a gravitational lens. What will happen is that a far distant object will be between. There'll be a galaxy that's in between us and a far distant object. And what you're observing with the near-term object, you start seeing a bunch of what looks like little galaxies around it. Well, what's actually happening is that the closer galaxy is basically gravitationally lensing the the farther galaxies picture around it and looks like multiple copies of the back galaxy, or some aspect of a picture of the galaxy. So this is an example of a gravitationally lensed, and it also has what's a hydrogen absorption line. So it gives me two. It gives a gravitationally lensed object, and it does have a nice absorption line also that you can observe. Now, one of the key things on this gravitation, this is that we actually measured it at 390.597 megahertz, and yet it was a 21 centimeter hydrogen neutral line. So this is an example of what Paul was talking about, is that the redshift from the expansion of the universe has actually caused a hydrogen line that started at X number of billion light years out is now at 390 megahertz. So that's a cool example, and this is in megahertz down here, right? That the whole spectrum was shifted down. You see the hydrogen absorption line drop. Okay, this is actually where a lot of the cablings are turning. This is Dr. Paul Sutter.
5 minutes.
He's been there for 30 years. Hello?
5 minutes.
Oh, 5 minutes. Okay, not Paul Sutter. Paul Perlmutter. Yeah, I think so. Anyway, 5 minutes. So let me keep going through. I want to do Alpha Centauri A and B, and then Alpha Proxima Centauri. All right, just because they have potential planets there, and I wanted to see if I can see them. This is an example of that, and there's a great example of A and B, and Proxima Centauri, which has our closest planet to us, exoplanet, is an Alpha Centauri C. Betelgeuse. I wanted to figure out what's going on with Betelgeuse. Didn't quite. You can observe asteroids. Titan is actually a calibration source. So Saturn's moon and Titan. M100 spiral galaxy, so you can see the spirals. More galaxies. Another galaxy, and this is from the ATCA, Australian Telescope Compact Array. So even though that's a smaller one, it has some very good uses on it. This here is what I was trying to go into spectral lines. So you can actually see different, you see basically radio velocity shifts, and even though that looks messy, that's actually because you're actually observing the radio velocity velocity changes instead of trying to get a single frequency. So it looks messy, but it's showing all those colors are velocity differences. Quasars, basically you just run through the quasar pictures. Now all these are online. This is another one that you can actually do the polarization on. So I got good polarization data. So you can actually do the IQU, polarization angles, etc. It'll actually calculate that with the data. So, and this is actually a known calibrator for polarization. So that was really nice. I hadn't done polarization yet in my analysis, so this is a real cool result for me to get polarization out of there. Another quasar. This is a binary quasar, I believe. And phase calibrator. So different phases. You always have to have a phase calibrator when you're doing that, when you're doing this analysis. So yeah, calibration is very important. So basically what you'll do is you have to tell them in your request what calibrations, what flux phase calibrations you're going to use, and then the computer will actually aim it at your source, and then it'll aim it at your calibrator. Then it'll aim it at your source, and it'll keep doing that. And so you've got multiple copies of both your sources and your calibrators, so the computer can actually, calibrate you in both phase and flux and polarization if you've got that kind of stuff going. So these are really cool protoplanetary disks. And by the way, some of this is now I'm starting to mess with colors. So I got a different color system set up here. Another protoplanetary disk. This one's my cool one because it actually looked very close to what the Wikipedia had, and you can tell the central star and the almost where the planets around there are eating around the medium that's around, so you can tell where they're carving out their slice in there. Just more, you guys can look at this stuff. It's all good. So what I want to do in the future is that right now I've got to the point where I can make pretty pictures. I can do some data analysis, but I really want to go into how do I get real science data out of this thing? How do I get quantitative data that I can actually make a paper or something like that and derive something, chemical signatures. They're really interested now in the ability to get, find different chemicals and, for example, protoplanetary disks to see, if they can find any industrial life or whatever like that they could find. Distance measurements. I'm not quite sure how to do distance on this yet. And moments. Now, moments are, basically your speed changes across all the different systems. And polarization in magnetic fields. There's tons of magnetic field work, especially in other galaxies, and you can derive a lot of information from magnetic fields. Okay, any questions? All right, I guess not. All right.
Richard, there's a question in the chat room.
Let's see. Let's see. You have traveled to take the classes, or okay, yeah. This year we did everything online. So we did the synthesis workshop online. So yeah, we just got done with it last week. So it was really good. I didn't think it was as good as being there. Because when you're there, you can sit there and the guys will come right over. The PhDs, and they're all PhDs, will come over, look over your shoulder and say, hey, why don't you try this instead of this, right? So I really got more advantage when I was sitting there trying to do this stuff. And these guys would actually sit there and look over my results and say, now try this command instead of this command, kind of stuff. That helped me more. Then all the different little, all these things have different little commands and stuff like that only they know, and they don't put it in books and stuff. So you just got to get some real time with these guys. All the data files are publicly available. Yes. All the data files that are not being held up, the new data files, no, because there's a time period for their the original guys who proposed the observation for them to write a paper on it and stuff. But after about, I think it's a year, then all the files get opened up. Okay, I think that's it. All right, let's see. Tom, are you almost lined up here? Let me stop sharing and I'll go give you a intro and
yeah, thanks.
Go ahead and okay. So Tom Hagen, electromagnetic compatibility test and design engineer, working in the automotive industry in the Detroit area. He has a BS degree in electrical engineering from Purdue and a master's degree in EE from Oakland University at Rochester, Michigan. He lives in Rochester, Michigan with his wife and 3 cats. All right.
Well, we're down to 1 now, but.
Yeah, that happens. Okay, you're on.
Okay, what do you guys see? Do you see my full screen slide there?
I see it. I do see it.
Well, thanks for having me as a speaker. I feel like I'm in a very distinguished crowd here. I hope I don't get too intimidated. But I don't think it compared to I think it was 2014 conference. I was actually followed, my talk followed a Nobel Prize laureate, Joe Taylor. that was a little interesting. So my talk today is about the low pheasant project, and I'm looking, well, we're all looking at McMath-Hulbert Solar Observatory here in the Detroit area. We're looking into possible collaboration on data reduction on this low phasm project. So anyway, low phasm is the low frequency all sky monitor, and it uses 12 of these dual dipole low frequency LWA antennas. The range, it uses 12 altogether. The frequency range is 10 to 88 megahertz. Antennas and front-end electronics were originally developed for the long wavelength array by the U.S. Naval Research Lab, University of New Mexico, Virginia Tech, and Jet Propulsion Laboratory. So the low phasm station is 12 antennas, and here I have a view of the very first one that was developed at the University of Texas, Rio Grande Valley, way down at the bottom of Texas. UGRTV is located in Brownsville, I believe, and the Port Mansfield site where the first antenna is about 60 miles away. You can see the site right down here. This is near the Port Mansfield Airport. So here's the site down here, and then here's the equipment shelter here about 1,000 feet away. Now, another one of these that's being built is being built at Hillsdale College, and that's about two hours away from McMath-Hulbert in southern Michigan. Here's a picture of their array. This is the standard 12 antenna setup, and excuse me, see a bit more vegetation around the site here in Michigan as compared to the one in Texas. The overhead view shows the array. It's sort of a Star of David arrangement, and that was done for certain beamforming reasons. The active developer there at Hillsdale is Dr. Tim Dolch. He's a physics professor. It was built with all private money. These systems run around $50,000 each. So it might be interesting for a smaller organization like one of our organizations that we're affiliated with to build. The reason for building this system is that it's intended to be used for transient studies. Everybody knows, I think, pretty much that transient studies are becoming a priority in astronomy these days, with things like fast radio bursts, gamma ray bursts, gravity waves, and so on. These are all very transient events. And in the optical world, we have a number of projects going. The Sloan Digital Sky Survey, for example, I believe was referenced in Dr. keynote speaker, sorry, the name escapes me. Featured in that. Then there's the Pan-STARRS telescope. It's also coming online. That one will be in Hawaii, I believe. Other optical arrays are the Meerlicht, came on board in 2018 in South Africa. Robotic telescope located near Cape Town. And then this observatory will be synchronized up with the new MeerKAT 64-dish array. So hopefully with all these systems working together, we may be able to capture more transients, including things like supernova, gamma ray bursts, fast radio bursts, gravity waves, and so on. So right now, there are 5 installations of low phasm across the United States. The first one was in Port Mansfield, Texas. The original station went in about 2015, I believe. There's one out in the VLA in New Mexico. There's another one at Goldstone Station in California. Fourth one is the Green Bank Observatory in West Virginia. I was hoping to see some of these this year, but of course, VLA conference got canceled and Green Bank is canceled. And then the fifth one, and the most recent one, was built by Tim Dolch at Hillsdale College in Hillsdale, Michigan. And Dr. Dolch invited us, McMath, Hulbert, and SARA to participate in this project. Ken Redcap and I are both volunteers at McMath Hulbert, and so I think through that association, he kind of associates McMath Hulbert with SARA, and I'm interested in pitching this as a citizen science project to SARA. It's fairly preliminary right now, but we'll see what happens. The stations are distributed geographically for RFI reasons, mostly. So if one station, of course, gets RFI, the other four most likely will not be affected by it, and then that data can be eliminated. The data from the sites could be used to create a gigantic interferometer at these low frequencies. And the interferometer configuration allows many small radio telescopes to be linked together to synthesize a much larger aperture telescope, as we saw in the last presentation. So the antenna is the original, basically designed, done for the long wavelength array. The first one being the VLA installation, 10 to 88 megahertz. So I believe they've got at least 2 of these LWA stations going now in New Mexico. I'm not aware of any more than that. Low phasm, primary goals will be low frequency radio transients and using field programmable gate array technology to implement a real full-time Stokes spectrometer and data recorder. The original array, many of us have seen this down at VLA, is this field of 256 antennas sitting off a little bit to the south of the hangar building over there, where they actually bring the VLA telescopes in and work on them. 256 of these cross dipole antennas, and the second station of this system is located about 75 kilometers northwest in the Sevalita Wildlife Refuge. So I've got a movie here that that was made with the long wavelength array. Just shows the capability. Is everybody seeing this now or not?
Yes, we see it.
Oh, okay. Thank you. Oops.
Seeing the movie.
Let me try this again. Okay, here is, this is from the LWA array. It's called, the site is called LWA TV. And this is a real-time image of.
Hi, Tom. We're not seeing actually the movie.
Oh, you're not. Okay.
No. Okay.
Oh, we're seeing the slide, not the movie.
Yeah, I see the slide. Yeah.
Okay, hang on. Sorry. I have to go back and change my share, I guess. Okay.
While he's doing that, and I got a, let's see, John McElroy, I was just sitting there almost belly laughing over that. We said we should hook up playgrounds everywhere into a huge array. So that was really good. And John Colt, Q for later, what is the electrical circuit for the cross dipoles? The two questions there. So
Yeah, that's coming.
all right.
Well, I guess we'll just skip that part. We'll go back to my presentation here.
Oh, that's too bad. All right. All right, your presentation's back? Yep.
Okay, thank you. Yeah, maybe I can get that going later. I've got another demo too that I guess I'm a little worried about. Anyway, here's the here are the electronics, the front end electronics. We have very simple again, and Whit Reed actually sells these kits. So we have people involved in SARA involved with marketing and building and marketing these things, I understand. So we have, this is basically half the circuit here. We have a hybrid combiner and low pass filter, gain, voltage regulator. And so we have a total gain of around 36 dB, noise figure 2.75 dB. It's not super, but then again, at this frequency range, you have quite a bit of noise from the galaxy already. So as I understand it, that's not a big problem so much. Here is another view of it. Then here's another view of the better view of the PCB. You can see the various components, and then the antenna connection points are these 4 pads out here. And so again, it's a fairly low cost setup. I think they retail for around $1,200 or so, from what I recall. So the 12 antenna array at 20 megahertz has a beam pattern that looks like this. It's pointing straight up with very low gain off to the horizon, which of course is where a lot of most of your RFI comes from. It comes from, horizontally across from various sources on the ground. Red is the highest sensitivity and blue is the weakest. The double ring configuration, we have six rings, 6 antennas on the inner ring, and 6 antennas on the outer ring. Oh, sorry, I need to go back here. When added together in phase, the region of maximum sensitivity is directly overhead. When added 180 degrees out of phase, the array is most sensitive to signals from the horizon, which of course we don't want. So in the software, we can manipulate this to get the beam pattern to what we need, which in most cases straight up, although I suppose the beam could be tilted if you wanted to follow Jupiter or something like that. I don't know. So anyway, we have here the inner ring and the outer ring, and the radius ratio was set up such that we have 441 centimeters radius on the inner ring and 763.83. Detailed information on how this was done is found in a paper. I believe I referenced it at the back of my paper. So from these 12 antennas, we have 24 signals coming in. We have the outer antennas, east-west polarization, north-south polarization, and then the inners, east-west and north-south polarization. polarization. These are combined in a combiner that sits out basically in the middle of the 12 antenna array to come up with an outer east-west polarization, outer ring north-south polarization, inner ring east-west, inner ring north-south polarization. So we have these 4 signals coming out from our 12 antennas, and then these 4 cables run back to the equipment shack, which is several hundred meters or 1,000 feet away typically. Then in the equipment shack, we have the 4 signals come in over low loss coax to the analog receiver board, the ARX board. We have buffered and filtered analog. Then we have a Roach board, which is a kind of off-the-shelf signal processing board right now. It comes from the University of California, I believe. Rubidium time base, synchronized by GPS for time sync, a good time synchronization. The output of the Roach board, which stands for Reconfigurable Open Architecture Computing Hardware, goes over 10 gigabit per second internet to the Linux PC for logging and uploading data, and then that goes to the internet. So basically this thing runs 24/7, or that's the intent, and it generates about 33 gigabytes of data per day that has to be uploaded to a central location. Let's see, here inside the Roach board, we have our 4 incoming signals. We sample at 200 megasamples per second. So we get our time domain signals, perform the Fourier transform. So we have frequency domain signals now, outer east, outer west, inner west. The correlator comes up with 10 correlated signals. So this is how the beamform is controlled, as I understand it again. We have autocorrelation signals of each one against itself. And then we have the 6 remaining cross-correlation signals. And then this goes over gigabit Ethernet to the processing and logging PC. What the full Stokes spectrometer claim means, as I understand it, again, I'm just learning all this myself. Basically, it means that the signals from each of the individual dipoles are combined in phase to synthesize the beam. The desired beam shape is to the vertical with minimal horizontal lobes. The 100 megahertz correlating spectrometer is using the Roach board, and again, the sample rate is 200 megasamples per second. A little bit about correlators for those of us who are not so familiar with all this. The correlation is a digital device that takes the Nyquist sample digital streams and basically it multiplies them with an appropriate time lag as desired. It can be programmed in. The correlators are basically the heart of all radio astronomy telescopes today, and especially with interferometry. It's a very, very significant process. The definition of cross correlation here is from the textbook definition we have. It's a time that it's done over time domain, and then that converts it to frequency domain. So we can this is a 2-way transformation. We can transform from time to frequency or frequency back to time for good signal processing. Autocorrelation is the same process, only you beat the signal against itself, and then this comes up with frequency domain power spectrum, again, as I understand it. The Roach board looks something like this. And it's an off-the-shelf signal processing unit from Berkeley Wireless Research Center. Xilinx field programmable gate array. I believe this system uses the Roach 1 board, which is probably not so state-of-the-art anymore, but it's more than adequate for the these purposes at these low frequencies. So here's some output that I guess Professor Dolch detected at Hillsdale. Here's an interesting one. You look at it and eventually you realize that this must be a man-made signal of some kind because it apparently has a very strong carrier signal with fluctuating sidebands off to the higher frequency range. This is looks like it was done over maybe half an hour or more, maybe 40 minutes, something like that. So data looks like possibly a digital TV signal, but the closest digital signal in this frequency range would be channel 2. The pilot is at 54 megahertz, 0.3 megahertz. So that's probably not what it is. It could be a military, excuse me, a military signal or something else. They've been over the horizon radar, 30 minutes duration. The lower diagram is a 5-minute event. So anyway, there is a possible transient. To my knowledge, they haven't detected any natural or astronomical transients. So anyway, Dr. Dolch has kindly provided data on his Google Drive for us. The files come out in compressed form, and the date and time of the file is keyed in the file name, so we have the date and time here. So these compressed files, these are 5-minute intervals here. Looks like the latest data that he has uploaded was back in March of this year. These are about 34 megabytes. And so for a whole day, there would be 288 files available for the whole day's observation record. And so we're looking at ways to handle this and actually go through this data manually and look for transients. I'm not aware if anybody's doing this yet. So, okay, here we go again. I'm going to try to do a live demo using the tools that are provided. So I'm going to stop screen sharing. And then I'm going to share, let's see. So Louis D'Artes, is everybody seeing my Linux terminal window here? Rich?
Yeah, we see it, Tom.
Okay, good. So what I want to do is I want to explain a little bit about these tools that are available on D'Artes's GitHub site, and these tools take the raw data files that we have available and creates graphic displays. I'm going to go in here and pull up this first one here. Takes a little bit of time. Okay, is everybody seeing this animated display? Apparently not.
No.
Okay. I've got a See it now?
Yeah, oh yeah.
Okay, so what this tool does is it scans through the all of the 10 output files and does an animation. This is a 5-minute animation, and it looks something like this. So I mean, something like this could actually be, I'm thinking, could be used by a student to look at all 12 or 10 files and possibly note a transient event. Now there's another tool that lets us look at the data for one correlation. And I'll have to share it again. Okay, so this is I guess, I believe it's one, yeah, it's one correlation. It's the autocorrelation from one of the polarizations. And this view allows you to view the data over time. So you can actually look at each one of these sweeps for a transient. Again, I think if we could provide these to students in some kind of an organized fashion so they could actually go up and daily go through these, I think it'd be a very fun citizen science project. And I'm hoping maybe I can catch some interest from, excuse me, some interest from SARA too, to do something like this. I think it might be a worthwhile thing. Back to the presentation here. Oops.
Can you go back to that original picture?
Which
that you were
one?
trying to get the one that you were trying to get the real data. Now that you know how to do it.
Oh, okay. Let me share that again.
I got two questions while you're doing that.
Yeah.
Ground preparation for the antenna.
Right.
And what is the cost of a roach board?
Roach board is around 10,000, as I recall. So that's a fair amount. Okay, I messed up here. Can't find my. Oh, here it is. This one you're looking for?
Oh no, the one that the original one that you were trying to get on. I think it shows the.
Yeah. Okay.
Yeah.
That one. Yeah. Now that I know how to do it. Hang on. Okay, now. Hey, bear with me for just a second here. Okay, here we go. Ready to see that? Yes? No?
Here you go. Yes.
See it? Okay.
Yeah.
So here's an output from the LWA array down in Socorro at the VLA, and this one's pretty neat. This one was done at, looks like 25.6 megahertz or so. And the neat thing about it is they happen to catch a Jupiter storm event down here. If you watch Jupiter, you see Jupiter flashing. Let me run that back a little bit. There's Jupiter flashing. Does everybody see that? So with this 256 antenna array at 25 megahertz, this is the kind of resolution you can get. But the plan, I guess, is to build a bunch more of these stations around. So we should, in the future, we should see pretty decent resolution at these low frequencies. This little noise spike up here, I believe, is RFI, possibly from an overhead power line in the area. So the LWA, you had a question about the grounding, did I hear?
Ground preparation for the antenna.
Yeah, it uses a, yeah, it uses a galvanized screen, and the idea there is to stabilize the impedance. I think I did mention something in my presentation. So once I get back to that, I think we'll take a look there.
Another question, can you set up your own LWA TV using Raspberry Pi?
I don't think that's possible, is it?
Well, let's see. Whit sent this. He's even sent a link.
Okay, so it is possible. Okay, okay, I guess we're back to the presentation now. Here's, again, just a rehash of this animation that you can use to look for. And the other one, the BBX, Explore BBX 2D.py program. Again, these are tools that you can easily download and install from the GitHub site. I'm running this on Windows subsystem for Linux. I'm not running dual boot or anything like that. And it seems to work pretty well. I had a little bit of trouble with getting it to connect to my Windows server. It's use a tool, an X server tool in Linux, and you fiddle around with it and you can get it to go eventually. So anyway, what I would like to do, or what I'm looking into, is to come up with a way for students to view this data and then manually look for transient events. To my knowledge, they're generating all this data, and I'm not sure if anybody is really looking that closely yet. So maybe this is a way that we could jump in and actually get some underprivileged students in the area involved, doing a little bit of astronomical work. A little bit about the McMath-Hulbert Observatory, where Redcap and I are volunteers and officers actually on the board. Also, this was established as a solar observatory in 1930 by a group of rather rich, wealthy amateur astronomers. They did pioneering work, movie work on astronomical events. They actually made movies of Jupiter's moons in orbit, shadows changing on the moon. They have caught the interest of the University of Michigan here in the area, and they were challenged to make some movies of solar events, and they actually built themselves a scanning solar spectroheliograph, and they put it in this first tower here. This is actually the first one built. These remaining towers were built over the next 5 to 10 years. This one was in Tower 2 is 1935, the tallest one, 1940. So anyway, it was in operation by the University of Michigan up to about 1979. It went into private ownership. It's on its second owner now. And he's getting to the point where he really wants us to do something with it. So we're looking at a significant, fundraising effort to actually preserve the place and maybe improve it. But of course, we need to have some sort of reason and to preserve it. And we're looking into STEM type projects, science type education projects with maybe underprivileged but deserving children. So what I'm thinking about is, since the McMath-Hulbert Observatory is near Pontiac, Michigan, which is a low income area, it gives us this opportunity to serve underprivileged students. Possibly we could set up a Galaxy Zoo type project with people set up to download the files and look for transients in the data. I would be interested in talking to SARA leadership if SARA would be interested in collaborating with such a project. And even building a low phasm array isn't that bad. It's relatively low cost, about $50,000 for 12 antenna setup. So even maybe a school district, a very motivated school district, could actually build one of these things. I guess that's about it for now. So anyway, the low phasm system is designed to detect fast radio transients in the 10 to 80 megahertz range. System is low cost. Smaller organizations could build a station. Ideally, when it's up and running, full function, we have 12 long wavelength array antennas with 24/7 watch on the skies. Geographically separated stations will eliminate false local RFI events. Data uploaded to a central location. Tools have been developed, which I think we could actually use right now to allow users to create graphical output and actually look for transients. And I think this project could make a great citizen science project if it were organized properly and managed properly. Thank you.
Okay, any questions? All right, I don't see any more questions on here. And that question about the LWA TV was not a question, it was a statement by Whitman. Got very good, Tom. Thanks, Whit. Let's see, great presentation from Step. Thanks, Tom. Great presentation. Perhaps NSF may have a grant for the education program idea. Bruce Randall, on CAS A and SIG A, they were flickering. Why?
Most likely that's atmospheric, an atmospheric effect. You know what HF is like for communications, Bruce. So probably that's transparency changes in the ionosphere would be my guess.
Okay. All right. Are the dimensions of the antenna published anywhere?
Yeah, these specs are all online. The circuit is online available. So, and if you don't want to build your own, I believe Whit would be happy to sell you one.
Yeah. All right. Okay, I think that's it. Thank you very much. Outstanding brief. That was really good.
Well, thank you.
And got that from Peter East. Thanks, Tom. Very interesting and informative. Okay. Let's see. And right on time, too. Wonderful. Okay. Our next, for the last one for today is Skip Crilly. Since 2014, Skip has been a volunteer science ambassador at the Green Bank Observatory. His job includes maintaining and improving the performance of the 40-foot educational telescope at Green Bank. Prior to this work, Skip was chief technology officer at 2 wireless equipment companies. Prior to that, Skip worked 27 years at Hewlett-Packard Company, developing test equipment for the communications industry. Skip has built and observed with numerous radio telescopes and interferometers. He built his first radio telescope while a teenager in Manila, Philippines, where he grew up. Skip's current interest is the search for extraterrestrial intelligence using radio. Okay, go ahead, Skip.
Okay, good. Can everybody hear me?
Yes.
Good, okay, great. You can see my screen.
Yes.
Screen's up. Okay, good. Super, yeah, thank you, Rich. Thank you for the introduction. I'm gonna give a presentation about SETI. I've been doing SETI for a very, very long time. Very interested in it. And something really fun happened a couple of years ago at a SARA conference when Rich Russel and I were talking about, wow, maybe we could do 2 antennas, the 60-foot Deep Space Exploration Society Plishner dish in Colorado and the 40-foot dish in Green Bank, where I work. And I had been going to Green Bank for about, 3 years when I started bringing my computer from home and looking for strange pulses on the 40-foot telescope while I was there part-time, maintaining the telescope. So we set up a system which is quite, I think, it might be fairly unique. I haven't talked to people who've done anything quite like this. The idea is that radio frequency interference is such a headache that doing single dish SETI is a really difficult problem. I've tried it for a long time and I concluded that you really have to have multiple separated antennas and look simultaneously. So in 2017, we started setting up a system. One is at Haswell, Colorado on the 60-foot dish, the 40-foot dish in West Virginia, and then starting late last year, we added in a telescope that's on my farm that I built. It's a 26-foot dish. The idea is to put computers on all three and run them autonomously, running FFTs, and they capture 1395 to 1455 megahertz in 3.7 hertz channels. And I have other presentations in SARA that I've given about the electronics that's in that system, and it's been upgraded over the years. But I plan to talk mostly about observations in this talk. So, if you have questions about the system, we can go into that. But I'm probably not going to talk too much about the system other than to say, it's a pretty conventional system that captures channels, stores them away. It has a signal to noise ratio threshold that stores to the files. So the way the system works is we get this distance separation, and because of the beam widths and also the Doppler shift, the differential Doppler shift between the sites, we can basically create an overlapping beam or set of beams that says, okay, if there's something here on one of the antennas, is it on the other antenna? And if so, how far off in frequency is it? So all of these are synchronized with GPS, frequency and time, and we have oven-controlled oscillators at the sites that all lock up the frequency synthesizer, the first LO. And if we go through the math on this, on the Doppler shifts, we come up with an idea that we can pretty much reject signals that are outside the beam, single beam, to about 720,000 miles. In other words, a source 720,000 miles out will be in all three beams on the same frequency at the same time as a pulse, and could be, we wouldn't be able to differentiate from anything closer. Now, if things are closer, they're going to triangulate or come in on side lobes and have various amplitude and frequency offset differences that should be discernible. Now, this is a very simple system at the start, and it is not immune to RFI. In other words, you could have side lobes in space that get into the antennas and then they produce anomalous results. So what I want to do is make sure that I point out that I'm a huge fan of multiple hypotheses, and this project involves lots of hypotheses. The first one I'm working on is just noise. I'm trying to say, can I reject a noise hypothesis using a system like this? And then over time, we can get into, okay, what about the RFI models and other possible explanations for simultaneous pulses on distant telescopes in narrow bandwidths, and then calculate likelihoods based on models for those things. So we've been running the system since 2017. Now, some of these observations I'm going to talk about, I've talked about in another SARA meeting, so I'm going to go through those pretty quickly because they basically got us started in a particular pointing direction. And this presentation is going to be entirely in that one pointing direction towards the star Rigel. that we have seen some anomalous results that are good for follow-up. Now, we started in 2017, and when I would go to Green Bank on my trips there as a volunteer, I would set up the computer there. And then Steve Plock, KL7IZW of the Deep Space Exploration Society, would drive to Haswell, set up there. And through February of 2019, we ran 135 hours of simultaneous transit scans at minus 7.6 declination. Okay, so we try to go around the clock. At the beginning, there were a lot of gaps. And then as time went on, I kept the system running the entire time, and Steve kept the system running the entire time. And then we did another 45 hours in April 2019. And then in December of 2019, we did 3 telescopes and accumulated, we added all up, a total of 290 hours of simultaneous observations. Each one of these lines is around 2 days, generally. There's various overlaps and things. Okay, so first I'm going to go through the observations up until February of 2019. So in all of those observations, after post-processing the separate files that had signals that were above a 12 dB threshold and were on the same frequency at the same time, in the same quarter second, because the interval of the FFT is a quarter second. We saw these pulses around the circle here in right ascension. And right away, I kind of noticed something interesting, that on consecutive days in August, which it turns out August was the first time we actually went through that particular right ascension, there were simultaneous pulses, and one of them was different by 1 hertz between Green Bank and Haswell, and the other one was off by 0.2 hertz from Green Bank to Haswell. And that's after I do the various metrology, and we work through the overlap of the beams, and we calibrate the beams using a using an NRAO 5690 as a calibration source. So it's roughly that direction at minus 7.6 declination is pointing towards the general direction of Rigel, and there's a few other stars in that area. So this has been a starting point to say, okay, let's continue running this, and let's keep looking in that direction. But also, we want to look at the other right ascensions as well, because they give us information about potential RFI and a potential noise hypothesis. And so what would we want to look for if we were to say, okay, what should we try to say is important to try to search for? And it turns out if you want to make a communication signal, you have to somehow make it different than noise. Now, the system for each one of the records that occurs, it stores all of the signal to noise ratio events that occur above a 12 dB threshold over time for each one of the bins. And it stores it independently for each one of the sites. And there aren't very many of these per quarter second. There's only about 10 to 20 of these events. So the idea is that if there was a communication signal present in this event, this would have to look different than noise. Well, this ends up being a Poisson process, an exponential spacing between pulses when there is only noise present. So I kind of started off by saying, okay, let's just look for things that are close together. Well, they're close together between Haswell and Green Bank, but then maybe there's also close together tones in the Haswell data by itself and close together tones in the Green Bank data. And maybe each of those has signal to noise ratios that also show some significance. Now, of course, RFI can look like this as well, but this turned out to be the first sort of easiest way to see if there's anything interesting. So this is what happened on one of those 2 simultaneous pulses. So the Haswell Green Bank August pulses, that one of them was at -1 hertz. And if we look at all of the records that occurred in Green Bank within plus or minus 20 seconds of that event, they're plotted in this plot here, where 0 seconds at the middle is the time of the simultaneous pulse. So at this time, there was a simultaneous pulse that was 1 hertz off between Haswell and Greenbank. And it turned out in the Greenbank data that near that time, there were quite a large number of unusual close space tones in the Greenbank data. So something seemed to occur correlated with that. Now, these pulses up above, these points up above, represent really the noise pulses, the pulses that exceed the threshold that are due to noise. And we can calculate the statistics of those and say, yeah, if there are tones that are only 607 hertz apart, and they ought to be a few megahertz apart, then that's an extremely unlikely event. So we can go through the probabilities on these things, and we come up with some very, very low numbers, indicating that there was something unusual in the Greenbank data at the same, within plus or minus 10 seconds, or 20 seconds in this case, of the simultaneous pulse. Okay, April comes around, and I couldn't find anything really close in the data for all of our April run. I did find a case where they were off by 5.8 hertz. Now, it turns out there's a very slight change in Doppler across the beam, and there's also some metrology issues that can cause a little bit of an offset. And there's also the issue that maybe communication signals are not on exactly the same frequency, or maybe if it's RFI, it's not going to be on the same frequency exactly. It's still worthwhile looking at to see what might be there, given that there might be something in the system that are happening. So in this particular simultaneous pulse from April that was at 5.8 hertz off, I looked at the spectra of Haswell and the spectra of Greenbank. And this is what we saw. The red lines indicate areas where there are very close tones. So you can see 2 tones here, 2 tones here. The upper plot is the Greenbank spectrum. Now these are spectra that were in the quarter second that the simultaneous pulse occurred. And you can see over here on the left that the simultaneous pulse occurred 5.8 hertz off is the low pulse here, and one of these 2. Well, it turned out that this one up in Greenbank had another tone next to it, very closely spaced. This one also had a high SNR on Haswell that was very closely spaced, and then there was another set closely spaced over here. So there was something there. There was also something up here, and all through this whole, the spectrum is sort of full of these highly anomalous events. In fact, there's a pair up here that are 1.9 kilohertz and 3.8 kilohertz off from a pair in Haswell, and the separation between these two is quite large. It's about 100 kilohertz. It's still a rare event in noise, but it's creating a very rare event, an even more rare event in noise at Haswell. So, you know, and another example is we could zoom in on the Haswell. Turns out this particular tone here is actually 2 tones that are spaced 1.66 kilohertz apart, which I had to zoom way out, and it still looks like almost one line. So this is the kind of thing that gets my attention and says, okay, something is unusual here, and noise doesn't seem to be working real well as an explanation. So then we did December 2019, running all the telescopes together. And this is a plot of the difference in frequency for simultaneous pulses that were measured in 2 and 3 telescope simultaneous observations. So I summed together all of the observations for all of the pairs. Now, there was nothing that showed up on all 3 telescopes at the same time and close to the same frequency. But between pairs of telescopes, there were, you know, quite a few that were within, in this case, I plotted at plus or minus 12 hertz. Now, if we take this area here from 4 to 6 hours right ascension, and we zoom in on it, we see down here that at 5.1 to 5.2, which the target direction is 5.1 to 5.4. It depends on the antenna. It's a little bit less for the 60-foot, obviously, but there's also pointing uncertainty. So there was a collection of pulses at negative delta F between the antennas that sort of got my attention there. Now, of course, there are others over here, so the statistical significance is maybe, is questionable. But it turned out that when I looked at these, I found out that they had a very close right ascension. So the idea is if everything was just right on on all three antennas, and everything was peaked up for signal to noise ratio, then we might expect that they would all respond with SNR events, threshold crossings, that are aligned with a particular right ascension. That's just a guess. It's just a wild guess. So I went and binned the right ascensions, and I came up with a big spike right in that area where there are 5 right ascension differences observed. Now, this is the difference between right ascensions. So in other words, how close is this right ascension of this pair between two sites to another one? And it turns out there's a big spike right here, which says, all right, what's happening in other right ascensions? Well, it doesn't seem to have that close a correlation to a particular right ascension. So there does seem to be something there. And, of course, this is a one way to look at it, look at the data and say, all right, what is the binomial of this? And it turns out to be a pretty rare event, which we would expect, because we look at that and we say, well, if there are that many right ascensions in that bin, right ascension bin, well then, yeah, it's way higher than the mean. So now I came home from Green Bank, and the idea was, I've got this dish on the farm, which, could I use one telescope? Is that practical at all? And so I thought, well, all right, let's see now. What could I do? Well, I've got 2 orthogonal circular polarized signals, and I've got 2 receivers that run simultaneously. And as it turned out, it only has 1/3 duty cycle. So I bought 4 more computers and 4 more digitizers. So I now have 6 computers and 12 digitizers, 12 channels of digitizing that are gigasample. I run them at 62.5 megasamples per second, and then I run them into a Linux C code that I've written. So I expanded the system to run 100% duty cycle on the telescope for the 2 orthogonal circularly polarized pulses, thinking, okay, there were a bunch of close tones in the April 2nd data that were close together. So maybe there's something strange happening where 2 orthogonal circularly polarized pulses might be close together. So this is a bunch of observations that I did after I returned. And the paper that has been submitted for the proceedings does not include the July data. So it goes up through the June 2nd to 5th data. So a few of the slides, if you're following along there, a few of the slides in this presentation will be after the June 2nd to June 5th slides that are in the paper. So this is what I'm looking for, is I say, all right, I'm gonna have a left-hand circularly polarized pulse at some time on some RF frequency, and then I'm gonna have a right-hand circular polarized pulse on another frequency at a different time. What's the difference in time? What's the difference in frequency? Those two are Poisson exponential processes that can say, all right, we can make this a pretty rare event. So if someone is trying to get attention, they might want to do this. They might want to transmit this. The other thing is, and this is very speculative, but if we look at RFI models and we can think about the models, we could say, yeah, does RFI do this? Well, normally RFI fills out the Poisson sphere. It usually has lots of high SNR events, so they're going to respond on both polarizations. So this is kind of a feed for RFI models that might be used to calculate probability. And I have not started that other than just, guesswork. So this is what happened in the February to March data for the two polarizations. And this was when I was running it at the 1/3 duty cycle with only 2 computers. And it turned out that in the 5.1 to 5.4 region on the 26-foot dish, there was a sort of an anomalous set of pulses close to 0 hertz now. These are not simultaneous pulses. These are pulses that were greater than 0.3 seconds in time between them with 20 transits. And I don't have the number for the maximum that I used on this. I'd have to look that up. So this is 20 transits that occurred from February 20th to March 11th. And the size of the dot is the signal to noise ratio. So you'd say, well, all right, yeah, it's happening in other places. And of course, RFI could look like something that happens with low delta F. So this is, this is interesting, but, it could be other things too. So then what I did was I rigged it up so that I could track the pointing direction, which I call this Hipparchus 24472, because that happens to be a star that's it's the closest star, it's a red dwarf that is in the pointing direction of the 5.1 to 5.4 region that we're interested in. And so what I did was I tracked for various amounts of time, close to like 93 minutes on June 2nd, where I tracked the 26-foot dish across the pointing direction in Asnell. And I did it on June 2nd, June 3rd, June 4th, and June 5th. And this is what happened with pulses that were within plus or minus 4 seconds. This plot says 5, but the limit is actually 4. Within plus or minus 4 seconds and within plus or minus 40 hertz of delta F, I saw this on June 2nd for simultaneous pulses. I'm sorry, I shouldn't call them simultaneous if they weren't exactly simultaneous, but sometimes I call these associated pulses. But it turned out there was a collection down here in this quadrant that seems statistically significant. And then on June 4th, there was a collection of pulses in this quadrant that seems significant. Not on June, but on June 3rd, it just looks like noise. And this is what I would expect. Now, these are the highest, this is the highest 8 signal noise ratios that occurred during the tracking. So while I was tracking this pointing direction, this is the highest 8 SNRs. This is the highest 9 SNRs. This is the highest 33 SNRs. And you can go through these numbers and say, well, yeah, even the highest ones like 1, 2, 3, 4, 5, et cetera, they look like they're uniformly distributed across quadrants, which is what we'd expect in noise. So there doesn't seem to be anything really here. And then on June 5th, there were pulses back again to one of the quadrants. Now we can do some calculations on this and calculate likelihood. For example, this particular set of SNRs has a noise model likelihood of 4 in 10,000 tries. So, of course, based on a, fair number of assumptions, as far as picking the endpoints, for example, I only picked the 9 SNRs. If I picked 12, I would have come up with a different number, etc. Okay, so what happened on July 7th to 10th? So basically what I did was I decided to not track for my next set of observations. And I ran it just for 4 days, allowing it to go through the beam without tracking, so transit only. And I said, all right, is there anything July 7th to 10th? And now I'm gonna get into what is called Bayesian data analysis. So what I'm trying to do is take a model and say, all right, we know a little bit about that model and we know what its likelihood is. And we have data that we know can fit that model, but we got to make sure that we can explain, that we can tell ourselves what is the noise model likelihood that it explains the data as opposed to the data given the noise model. And this is using Bayesian data analysis. That's a based on Bayes' law of probability, that allows one to update a model's likelihood of explaining data, given that we have information about the model, noise model is valid, new data that we take, and there's also a factor which is necessary, which is that the data itself is valid. For example, if the data isn't valid, well then it's got a low likelihood and this whole thing explodes, and then everything looks like it could explain the results. So this had two quadrants on the with 3 outliers here, with pulses that appeared to be in this quadrant at the highest 10 signal noise ratios. So I use this to say, and by the way, if there's anyone listening who is a statistician and knowledgeable about Bayesian data analysis, please let's communicate, because I want to learn more about this. So the idea is that I create a model and I say, all right, the highest 10 SNRs tells me there's a model that there's something happening between these two quadrants, quadrant 2 and 4. So now let me take the next highest 40 SNRs as new data that is based on that model and say, what's the likelihood that fits it, apply the Bayesian formula in Bayesian data analysis to update the original model. Well, the original model here has a noise model likelihood of 0.12. So we'd say, all right, that doesn't really tell us very much, because noise could do that, and we could have just stumbled across one where it happened. And then the idea is that after we look at this data, we have to multiply by 0.08 for this data, which is just the data given the noise model, and it reduces the probability that the noise model explains the data to 0.01. Now again, this is not a very, I would call it low value, because we could have just stumbled across it again, just by chance over these 4 days. So then I took the 4 days, July 11th to 14th, and a really strange thing happened with that data. Each one of these numbers, 1, 2, 3, 4, is now the day, not the SNR level. This is the day, 1, 2, 3, and 4. And a weird thing happened. There was a huge concentration at minus 1.75 seconds for a whole bunch of pulses, which also says they were in this quadrant, not these two quadrants, not only in these two quadrants, but all at the same 1.75. Now, this has a very low likelihood by itself. So, that's one issue. But then what we can do is say, all right, let's apply the noise model and let's measure what happened for the 13th to the 40th ranked SNRs. So this is the highest 12 SNRs. These are all the SNRs below it. We're going to call that a new data set, and we're going to compare it to the model. And it turns out those SNRs were concentrated in another set of quadrants, quadrant 3 and quadrant 4. Still a very unlikely event. You can say, all right, there's 6 possibilities of other quadrants we could take, in pairs. So we got to multiply that by 6, and we come out with the numbers. And it turns out, because of the way this is distributed, especially in this value, the noise model explains this quadrant concentrated data. It's extremely unlikely. And so, because it's generally the case that hypotheses need to be refuted, they almost can never be totally proven. Refuting a hypothesis or a model is an approach. This is a very low number and says, yeah, noise doesn't quite explain this. Well, what about RFI? Could there be a RFI where a circularly polarized pulse shows up on one polarization and then the other one separated by 1.75 seconds at these various differences in frequency over a period of 4 days, and while we were looking in the direction of Rigel? So that becomes the next thing to look at. So the first thing I looked at was, all right, what happens with I didn't take all right ascensions, but I took right ascensions from 1.8 to 6 hours. And I said, all right, is there anything at 1.75 seconds? Maybe there's an RFI source that outputs opposite polarizations at exactly that time. And we look across there, and there isn't anything really significant. There are no lines that are jumping out and at the 1.75 second point. So this doesn't quite fit that it would be noise that would occur at some other time, explaining this. And then this is just another view of the of that quadrant data that I showed earlier, which shows that at the highest SNRs, there was this concentration down here. And then when we look at the 1.8 to 6 hours, we say, well, we don't see any concentrations like high-low that are kind of spotty at other SNRs over the 1.8 to 6 hour period. So now it'd be possible to go back through this whole thing and check every 0.3 hours of right ascension, and that would be a good follow-up additional thing. But getting into the idea that that's an RFI model, so not a noise model. The way this is looked at is we say, no, it's noise. Everything we're looking at other than maybe an interesting pointing direction is noise. So I'm going to leave this one up for a couple of seconds because this is the July 15th to 18th, 2020 near Rigel anomaly, pointing anomaly that's similar to the other ones. I took the lines off the graph, you know, make it look, and each one of these numbers, 7, 8, 5, 6, 7, and 8 are the day associated with July 15th to 18th. And it turns out I found an anomaly in here. Does anybody see something that looks anomalous in this data? I'll give you a hint. Just, you know, start with -4 seconds and then just work your way across and say, is anything happening at a particular time on all of the days, and maybe with some kind of frequency concentration? Okay, well, I'm going to move along. I'm sure by now some of you have seen something kind of very unusual. And there's an unusual concentration, and it turns out to be at 0 seconds. Okay, now 0 seconds is one of those things that I get a little nervous about because 0 seconds of offset between two polarized right hand, left hand is linear potentially. So linear RFI could easily have caused this. But there is an anomaly in here that has a noise likelihood event of 6 in 10,000 tries. So there is there's a need to find out what is causing this because noise does not seem to fit. Now, before I go on, I just want to mention that I do have an RFI algorithm that rejects simultaneous durations on a particular frequency. Okay, it's basically a dwell algorithm, and it says if something dwells on one frequency, then reject that 1 kilohertz band. So it automatically goes through in the post-processing, and it rejects anything that lasts for more than a particular amount of time, and those are all parameters that I put into the RFI filter. They basically say, no, I'm looking for things that are on different times and different frequencies, not concentrated at one time or one frequency. So, so then July 19th to 22nd comes along, and I go, well, all right, okay. Are high SNR anomalies happening every day? So it turns out in the 4 days of this data, there were high SNRs on this day, the last day, and the day before there were very few high SNRs, again deviating from what we would think is a really exponential type of distribution for Gaussian noise. So this has an interesting sort of thing, and again this has a very low likelihood. And then if we go look at all the other, right, not all the other, but over 2.3 to 6.5 hours, we find, oh, look, well, there's another one right there. There's a gap between these 2 days where this occurred and this didn't, but it's at a different level of SNR. This is highest SNR, lowest SNR. It's at a different level. It's a little bit narrower gap than the other one is. And of course, it's also, I could have picked any of these all along the way. So the likelihood is, you know, I have to multiply by maybe 6 or so or 8 in order to compensate for it. I could have picked any of these to try to find that particular one. So this is all interesting, and sort of saying what's going on. So the idea is that the noise model doesn't appear to explain the data very well. Now, I could be making a mistake on my noise model, and there could be other things going on. So these anomalies compel further observations. And I got to the point where I've said, well, you know, I can't do much more with only one telescope here on the farm. So I'm building another one, and then I'm building a third one after that, but that's in the plans. So I'm building a 28-foot diameter under construction. And what I want to do is put it about 100 feet to the east from the dish that I currently have, and say, okay, something, if it's there on the 26-foot dish, it better be on the 28-foot dish. Now, it also turns out that my 26-foot dish doesn't have surface accuracy that's all that great. So it has a low efficiency due to that. It's about 0.4 just due to surface accuracy issues. And so what I want to do is make this one have better surface accuracy, which means it should have a lower splatter type side lobe in offset from the main beam, and also pick up sensitivity, about 4 dB of additional sensitivity over the 26-foot. So with this antenna running at the same time, I should be able to see, well, if it's really there on that antenna, on the 26-foot dish, it better be on the 28-foot dish as well, if it's in the beam. And then the other thing I can do is depending on the signal to noise ratio of the pulses, I can say, all right, can I measure the phase difference? Now, it turns out these are broadband signals that are popping up in this data. So it's possible that if you get a flurry of pulses that are occurring, you can measure the phase difference without the ambiguity due to the aliasing that normally occurs when you only have 2 antennas in a direction finder. So I'd also like to have 3 synchronized telescopes. We also are planning in a couple of weeks, we'll be doing another Haswell, New Hampshire simultaneous operation. And then there's also a plan to start observing with the Ohio State University's Project Argus telescope. So they're working on a plan to simultaneously point that telescope. You may be familiar with that. It's an all-sky phased array that uses various algorithms to search the whole sky for pulses, and also can do beam forming, multiple beams simultaneously. And the idea is to work on the RFI models, get satellite experts' ideas, and encourage others to try these things. They're not too difficult to do, and given that my 26-foot dish is actually not a, it's got about a 4 dB down surface accuracy issue. A smaller antenna is probably possible to see some of these same unusual events. So the idea is to try to keep looking at this. So this is a picture of the 28-foot dish under construction here. It's gonna be pedal based as opposed to the other one, which I just climbed all over up in the air, putting mesh on it. And this has one of the rectangular pedals along with the 7 of the 8 circular pedals on the 12-foot central section. So there's going to be sections here and then triangular sections that I have to add the whole thing. And I did want to point out that on my farm, the animals, I basically rent this place from nature. There's a porcupine over here. It's not in the picture right now, but this is its dinner area. When I set up to do optical telescope things at night, I'm using a chair that's pretty much in that spot right there. There's a hornet nest in the telescope base. This is a trailer that's going to be the telescope base for the 28-foot dish. I use the trailer as a rotating base for azimuth control. And this in the background here is another trailer that I'm going to use for another telescope. There's a giant hornet's nest in this thing, so I'm going to have to wait until it's very cold before I can get anywhere near any work that I need to do. I need to install the elevation axle on some scaffolding that I attached to the side of this. There's a robin nest next to the front door right here, which it turns out now has a chick as of a couple of days ago, but I'm not going to go anywhere near that. In fact, when I saw the robin sitting in it, I decided about a month ago to not even use my front door. And so I haven't gone out my front door. I have to go around. It's a little bit of extra work, but not a big deal. And then a couple of days ago, both of the optical links, so I run fiber optic cable. I use RF over fiber from the dish that goes through this pipe here, this long pipe. Well, critters love to get inside of pipes and you know, make homes and such. And it turned out some kind of critter, probably a mouse, ate my fiber optic cables in the middle of the night out here about 3 days ago. So I had to go out there and fusion splice the fiber optic cables back on it, kind of the whole thing, finding it, et cetera, doing all that. So that's these are challenges, but this is an enormously fun project, and we'll see where the data takes the project. So I'd like to really thank Steve Plock, KL7IZW, who operates the Haswell system that's installed, and just all of the Deep Space Exploration Society team, Green Bank Observatory team, Ohio State University team, and family and friends. And thank you all for listening to this. Thank you very much.
Great, thanks, Skip. I got one question. Dish has a right hand and left hand circular question. That's a question. Could combine with various amplitude and phase to get any polarization. Should be possible to establish polarization of each event. Possible, useful.
Yes. Oh, sorry. Is that question goes on?
They're all questions.
I'll answer that one first. Yes, that's a great idea. One of the things I did was to say, in order to measure multiple polarizations, I need FFTs running on each one of those points on the Poincare sphere. Turns out it explodes pretty fast. If we want all the 4 places on the equator and right and left hand, we end up with 6 times a single channel. So what I decided to do was to say, all right, I got to start somewhere. So I'm going to start with right hand, left hand. Now, normally what happens is if somebody wants to do a polarization modulation or something like that, use polarization for a purpose, they might be likely going to choose right hand and left hand because it tends to not get disrupted by Faraday rotation in the atmosphere. So that's just a guess as to what that is, but certainly yes, that's a great idea. And with more processing, that would be a really important thing to do.
Okay. Ted Klein mentions that trailer frames to rotate dish is kind of like Jansky's antenna.
Yes. I actually built something like Jansky's antenna in college, but it didn't survive the winter. But yes, the idea is it does rotate on 2 wheels, but they're closer together. And then I have electric SUV, four-wheeler winches. So basically winches you mount on the front of a four-wheeler. I've got a bunch of them operating all over. There's a YouTube video on YouTube. If you just go to YouTube and type my name, you'll see the design of that antenna. I go through it.
Great. Anybody else have any other questions? That's all I got on chat right now. Okay, well, outstanding, Skip. This was very fun, and I've seen a couple of these things, and this is always I learned a ton of stuff every time you present this. So thank you very much for that. And
thank you. Thank you.
And okay, all right. We are in raffle number 3, break number 3. So here's the plan, everybody. Let me do the raffle, and then at 1800, which is about 48 minutes from now, we'll do start the virtual Drake's Lounge for 2 hours. And if it stays longer and people want to talk, then I may keep it up longer. Okay. And but let's do the raffle real quick. So the first raffle winner is Wanda. Wanda Waters. Wendy Waters. Is Wendy online? Let me see if she's even logged in here. So Wendy, are you online? I see your.
She shows as being logged in.
Right. Okay, well let's go to the second one.
Wendy is in the chat. She says she's here but no audio. Maybe you talk by
Okay.
chat.
Great, Wendy. Let me share real quick the options here. Audio's that's fine. Using that, let's see, right there. Okay, so the question is, what prize do you want? Skip, I got it. Dave Fields, good work. Wendy wants the Radio Astronomy 2nd edition. Okay, great, Wendy, you got it. Okay, the next winner, we got 3 of them this time. John Tiller.
Hello, I'm here.
Hi, John. Here's the list. Let's see, let me get a radio astronomy one's gone. Which item would you like?
Rich, I'll take the SARA mouse pad.
Wow. Okay. All right. Number 14, SARA mouse pad. All right. Okay. The last winner for this round is
What is the winner of the mouse pad?
that's John Tiller, number 14 on the list. Okay. Okay. The next winner is Marian Zabo, S-Z-A-B-O. Marian, are you online? Okay. Do you see her on? Is she on logged in? Let's see. Stand by here. Let me see if she's even logged in here. Oh, doesn't look like she's logged in. Let me do one more. Okay. Okay. Stand by. I'm having trying to get out of. I might have to get out of share here for a second. Okay. Okay. Yeah. I have to use my my fancy random number generator. So number 27 is Ken Redcap, our outgoing president. This was not even set up.
No, he's not here because of personal family problems.
Oh, I'm here.
Yeah, he just showed up.
Hey, Ken.
Ken.
No, they finally let my dad out of the hospital, so life's back to somewhat normal.
Oh, excellent. That's really good news.
So,
Okay, Ken, you are a winner of something. What would you like to get?
wasn't there, can you show me that list again, please, sir?
Yeah, let me go back here. That.
The Radio Sky.
Okay, so on that, you get one license for a particular, let me go to those options there. one of those products. Radio SkyPipe, Radio Eyes, or Radio Jupiter Pro.
Oh, okay, one of those.
Yeah, so it's one license for one of those.
Okay. The sky pipe.
SkyPipe, okay.
So,
Okay, Ken, good job.
okay, thank you, sir. And this is turning out quite well. It's an interesting way of doing it.
Well, we had to have something for your 20 years of service at SARA, so a free radio SkyPipe is congratulations.
Well, I can use it. Thank
All
you.
right. Okay, that was it for this raffle. Everybody take a break. Come back at in let's see, about 41 minutes, and we will start. We'll just stay on Virtual Drake's Lounge. That's a sort of a free. I'll moderate it, and keep the goal is to introduce everybody, sort of share what items, things you got. You guys can use the interactive chat privately to your heart's content. Now, I'm just going to leave all that up, so you can use that now and all through the Virtual Drake's Lounge, and have a good time getting to know each other. Okay, so I'm going to go offline, but you guys are still on if you want, and you can communicate through chat. Okay.
I don't think you can go offline without.
Oh, I'm not going offline. I'm not going offline. I'm just going to turn my video off.
Okay,
Yeah.
okay.
Yeah.
You want to put the schedule up?
Yeah, that's what I'm doing. I'm even going to annotate it because we learned how to annotate in our training sessions here. How's that? Pretty good, huh?
That'd be low, so.
Advanced Zoom training, like Paul said, you have to do this for a living.
Well, I've learned one thing during the conference today. I bought a speaker from Amazon that will be delivered tomorrow. Speakers in my little laptop are just not good with my ears.
Oh, yeah. What time are we starting up tomorrow? That's 1300 Eastern Daylight Time.
Eastern time, whatever.
Eastern Time. And now, is that hurricane time? What time's your hurricane hit?
About 2 o'clock.
Is that today or
Tomorrow?
Tomorrow, okay. So just an hour before the hurricane hits, we'll start up again. So
Yeah.
you guys have something to do during the hurricane.
Yeah. I'll have my bottle of medicine next to me in case I need it.
Same link as today. Yes, this will all be the same link. You should be able to just log on just like you did today. And don't forget to vote.
Does that need a special prescription there, sir?
Special prescription.
For his medicine.
And that's some kind of hurricane prescription, I guess.
Oh, Don Julio? Oh, well.
I'll have my buddies, Jack and what's his name? Can't remember. Anyway, I'm fine. Don't worry about me.
You'll be feeling no pain. Okay.
If we see something come through your window when you're online, we will call somebody.
I'm trying to be very careful to not let anything show on my video. Got to make sure I keep my pants on and everything. Hate that part.
Oh, we did have some.
David Westman, I'll send email address, his mail address to you.
Okay, the recordings probably won't come up. That's for Bill Miller. Will probably not be up today. I think we got to, in fact, let me turn that off. Thanks for reminding me. I still had the recording going. We will probably not have it up today. We got to go and